Hi guys, welcome to this fourth tutorial using the MBA combined data, and today we are going to interpret the results of the mixed model that we have created. So for today's tutorial you'll need the interpretation workbook open and the script open in SAS. And without further ado, let's go straight into the script in SAS. And we are going to go down to the very bottom, and the model that we are going to run starts on line 178. So what we're going to do is we're going to add some pairwise differences into this model to get an understanding of what the differences are between seasons, which was the original aim of the model. So you'll be familiar with the first 10 lines or so of the model, whereas the LSM estimate season may be a little more different. And what we've done in this LSM estimate season command is we're just looking at the differences between seasons. So as you can see, when we just want to estimate season 1, we just use the brackets and put 1 for the portion we want and 10 for the element or the element of the class that we want to use. To extend that to a difference, all we need to do is use 1 for the first season and then -1 for the second season. So if we want to look at season 2 minus season 1, we take the appropriate element for season 2 and take one portion of it. We then subtract one portion of the appropriate element for season 1. And you can see this here again for season 1 to 10. We're just taking this element 10 for the first season and subtracting element 1, which is the 10th season. And again, just to reiterate, this looks a bit different to the spreadsheet that we've used because the categories are in reverse order in SAS compared to what they are on the graph that we were looking at. So from our 10 seasons, season 1 was actually equivalent to element 10 on SAS, and season 10 was equivalent to element 1 on SAS. So let's run the model. Okay, so here's the model output, and we'll be familiar with all of the outputs now, having gone through it on multiple occasions. You can see we've got the least square means estimates for the first function we use, which is just all of the season's estimates, and then the second one gives us all of the differences that we asked for. So from here, all you need to do, or all I have done, is I've highlighted whichever element I wanted and then copied it into the interpretation spreadsheet. And you can see I've taken the covariance parameters, the least square means estimates for each season, and the least square mean estimates for the differences. And I've done that so that we can do some extra work with it. For example, we might want to get the pooled standard deviation so that we can work out Cohen's d effect sizes. And in order to do that, all we do is we add these two numbers together and square root it. And it's really important that you square root them when they've been added together rather than square rooting them and adding them together. And I'm going to show you that difference now. So if you square root the number first, you end up with a completely different standard deviation. So always add the variances together and then square root them to get the standard deviation. We could also look at the standard deviations for our between position and within position. And again, this is just a square root of these variables. So square root here, then for the lower and upper, we're going to square root 7 and square root the upper. Same again for the within position, square root 67 for 8.23, and then your lower and upper, just square root these two numbers. We've also calculated the confidence limit difference, And the easiest way of doing this is just take, with the least square means estimates, because they're normally distributed, is just to take the 96 centimetre upper and subtract the estimate, and that'll give you the difference on both sides. And finally, we've calculated the effect sizes, and the effect size is just the estimate of the difference divided by this pooled standard deviation. And you can see all of the effect sizes here, the lower and the upper intervals for them. Okay, so what does this actually mean? So when we look at the results, we want to look at this p-value, the estimate lower and upper, and also the effect size. And we can put all of this together, for example, with this statement for the first estimate. So although season 2 had a lower jump height than season 1, so you will find this is the first number is always a reference. So if a number is negative, that means the second number is bigger. Okay, so although season 2 had a lower jump height than season 1, and I've just taken these means from here. So you can see 90.3 plus or minus 3.7, and then 92.2 plus or minus 3.81. The difference was non-significant. So again, using this p-value here, we have a non-significant difference, and then give the effect size values for it. So even though we know that season 2 was less than season 1, it wasn't different enough for the difference to be considered significant. Next up, looking at season 3 and 2, we can see there's not a massive difference there, so it's a lot more clear that the difference was non-significant. So really simple comment, there was a non-significant difference between season 3 and season 2, and apparently I can't spell significant. You can edit that for yourself in the video. However, when we look at the general trend from seasons 1 to 10, we can see that season 1 is 4.7 centimetres greater than season 10. And if you eyeball it, you can see that as well. So, and that is a significant difference. So we could call that jump height season 10 was significantly greater than jump height season 1. We have a p-value, we put our effect sizes in, and using the effect sizes suggested by Will Hopkins, that is a small effect size. Using Cohen's effect sizes, I think he had 0.5 as moderate, so you could put moderate there if those were the effect sizes you were using. And it's all well and good giving you those comments, but what does that actually mean? Well, we can have a look at what that means and have a look at some interpretation. So when we look at the 10 seasons as a whole, there was a small difference in jump height. However, between consecutive seasons, no significant differences were found. And you can see that the P ranged from 0.12 to 0.92. And the interpretation of this, I believe, is that there was a steady longitudinal increase in jump height, but it was slow and steady. It didn't just happen overnight, you know, as training practices increased and improved and understanding of nutrition improved perhaps over the last 10 years, that could result in better athletes being formed. But this happens slowly and steadily rather than, for example, between 2 years and then staying static around those two years. And then we can have a bit more fun with it by looking at the random effects. So these values here that I've got for the within and the between position standard deviation, as I say, have come from here, which is just the square root of this part. And we can see that the within position standard deviation is greater than the between position standard deviation. It's actually almost twice as great, which is why the almost is there. So it's almost twice as great as the between position standard deviation. And this suggests that variation in jump height performance was greater within positions and between positions, and we saw that. We showed that with the centre and seeing how far around the estimate for centres the observations were. And this could be due to jump heights differing with the roles that players play in the teams rather than the positions themselves, or it could be that players are still maturing, so over time this will reduce if we look at actual NBA players. And we can do one more thing to get an understanding of the help that the clustering gives the model, so how much variance is due to the between position clustering itself if we consider the intraclass correlation coefficient. And the intraclass correlation coefficient is just equal to the between position variance divided by the sum of all the variances. And to give that a quantification, you can see that approximately 0.2 of the variance in the model is described by the between class differences. So there's a lot that happens outside of those between class differences to cause the variation in jump heights. And that's it for this look at the NBA combined data. Next, we are going to look at some athlete monitoring data.